Okay, let's get started. So this is Sim ED administration, computer simulations to keep your department moving and avoid disaster. My name is Josh Joseph. I am the operations director for the Beth Israel Deaconess Medical Center Leahy Emergency Medicine Network, and I also teach at Harvard Medical School. I have absolutely no disclosures, but I'm totally open to them, so please contact me after the talk if you have business. So we've all had the experience heading into a busy 5 p.m. shift or 4 p.m. shift. And for those of us who work in operations, it's not that unusual to suddenly get pulled aside, even though the waiting room, which here is a nice, polite Canadian waiting room, and this is maybe a more realistic looking waiting room from one we're used to, you get pulled aside working in operations, it's hospital management. Guys, we have a problem. Lengths of stay are getting way out of control, and we've been doing some analysis. Looks like there's one problem, and that's the CT scanner. We figured out that it takes about 18 minutes to get a scan, about 3 scans get ordered per hour, and there's a huge discrepancy. Even though there's only 18 minutes per scan, we're seeing like 162 minutes from order time to scan time. Tons of people are waiting, they're getting upset, really don't like waiting for that big fancy CT scanner we gotcha. Before you can even say, hey, maybe there's more to the story, Chief of Surgery barges in. All right, I've got a solution to this problem. We're going to get a big, shiny new CT scanner. As it happens, we're not picking up enough cases of appendicitis. It's going to be beautiful. It's going to be 64 slices. We're going to give every single patient rectal contrast. We're going to see more appendices than you could ever imagine. We're going to operate day and night. We're going to make it rain. Admittedly, we need some space for the CT scanner, so that break room you guys have been using, that's got to go. So we look at the details of this new proposal for how we're going to fix the CT bottleneck. Got a 64 slice modern CT scanner. The outlay is going to be, let's say we make some deals up to $700,000. There's going to be some money involved setting up all the new wiring, getting rid of all that coffee machine business in the break room. And we're going to need some people to run the CT scanner. So that's not going to come cheap, but we'll round it off about $1 million. Lots of pros here. It's shiny. We'll get to do more surgeries, bring in some money for the hospital. There's some cons too. We'll be realistic. The rectal contrast is going to really push the turnaround time on those scans. And especially, maybe the stroke codes won't like it so much, but hey, they might have appendices we can take out too. So it may be win-win. And again, the Prescani scores, well, that's an ED issue. The chairman of surgery reassures you that's only for discharged people. And hey, people who we find appendicitis on, they're going to love us. So what do we do? Well, okay, you quickly counter-propose. Why don't we get some more CT staff going? Let's pay them some overtime. Let's really try and kind of get them to play along, try and bring those turnaround times somewhere a little safer. We'll budget out about $55,000 for each additional hour of coverage. This is looking at a yearly sample here. And you get something for that each hour. You'll get, the turnaround time will come down within reason, but about 1 minute per hour in terms of the actual scans. So we actually, in reality, looked at an issue just like this because even though nobody was proposing that we rectal contrast everybody in the emergency department, we at our institution had some major issues with turnaround times for CT. We really didn't have a really good sense of how long any one CT scan was taking relative to the timestamps that we had in our EHR, and also where that time was kind of being lost or wasted. So we sent an intrepid operations fellow to time CT scan after CT scan with a stopwatch. And looking to the world of queuing, we found there actually is a solution for trying to figure out why we're losing all of that time. It turns out that even though you can line up the amount of time a scan takes and the amount of time in between patients pretty reasonably, reality doesn't always reflect a neat ordering of arrivals and scans. A lot of times there's some serious variability. And this is really a huge issue for patient arrivals because we really can't just run the CT scan at a constant rate. We have to run those scans along with when the patients are showing up for them. And invariably, you don't make up the time you lose. If you have to wait, if you know that you're getting a certain number of patients per hour and you have to wait to see them, you are going to lose time whenever there's not somebody to be scanned. Similarly, if you get a batch of patients in a row, if you've only got the one CT scanner, there's no way you can avoid at least having a little bit of a wait for those people. Again, if two people show up and you only have the one CT scanner, there's going to be some wait. So some wait is unavoidable, but you really need to think about a way to program in that extra buffer. So it turns out from queuing theory, there is a solution. There's in our long model, and looking at something called a Markovian queue for a certain number of servers. I'm not going to hit you over the head with math because the math gets very complicated. But fundamentally, a Markovian arrival process means that these arrivals are independent. Patients do not conspire to get CT scans together. And generally, we'd like to think that whether you order one CT scan on one patient probably doesn't affect whether you order one for the next one. Arrivals, as I said, are independent, but we're also saying that the service times are independent. This is a little bit of an assumption, but we're saying that the CT scan tends to run the same way for most patients. Again, we're ignoring different kinds of scans we do here. We do a whole lot of math, and the beauty of this is that we can come up with a simple equation that lets us take something pretty concrete and come up with a good prediction for how the weights are going to run. This is the utilization ratio. And all it really looks at is how fast are we providing a service and how fast are arrivals coming? How fast are we getting demand for that service? And the magic number for utilization is 1. This is fairly straightforward. If you're getting more people than you can serve, then weights are going to explode. Again, there may be periods where your utilization goes up beyond this, but if you're consistently above this ratio for a long period of time, you're going to get into trouble real fast. So we built a calculator where you can simulate a queue like for a CT or for many processes in the ED. If you go to edq.org right now on your phone, on your laptop, you can actually run the simulator as we speak. And what you can see in real time is how the distribution of patients waiting build as you change the turnaround time. So again, with a model like this, you can get a good probability distribution for over time, how many people are going to be waiting, how likely that group of people is going to be waiting, and you can provide some real orders around how likely it is that you're going to get a major wait. Again, you can't predict the future, but if performance is fairly consistent, then you can guarantee a level of service, which is pretty good. And again, to look at how waiting time tends to build as utilization approaches 1, that's that asymptote on the side of the graph, you can guarantee a pretty consistent level of service provided you know how long that service is going to take relative to how many arrivals you tend to get. So let's go back to our bottleneck. Is the chief of surgery going to get the fancy new scanner with the rectal contrast? Well, let's price out our option. So as we saw, if we're talking about $55,000 for each hour of coverage, which brings down our turnaround time, if we, as in the little example I showed, bring our turnaround time from 18 minutes to 12 minutes at a cost of $330,000, so not cheap, but not $1 million as far as the math I can do goes, we're going to bring down the average wait for CT, again, at times where our arrivals stay consistent, from around 162 minutes to 30 minutes. Not a bad deal. So again, as I mentioned, this queuing process, the simulator that we have, works for many kinds of discrete processes in the emergency department. Now, what's a discrete process? This is a process where you have a single encounter and you provide a service of one sort or another in one go. You're not looping back to do it over again to check results. And again, this isn't the perfect model for your whole stay in the emergency department, but it is really good for a lot of applications we look at. CT scans. Usually we don't do partial CT scans. You either get it or you don't. Same thing for lab tests. And this is more talking about individual lab tests. You get the troponin result and it's there. It takes a set amount of time. The time may vary a little bit, but at the end of the day, it's one chunk. And there are other parts of the workup that we do that really fit well into this model. Triage is a perfect example. Admittedly, sometimes you might start and stop triage, but for the majority of patients, triage is a one and done kind of process. And then there's physician throughput. That's a much, much bigger issue. Now, this can work. So the OG paper for looking at this is Linda Green's examination of queuing theory, looking at individual patient arrivals and how long it took an emergency physician to see them. You got some pretty damn good results. So within the study period, she looked at using a queuing analysis to project a new schedule for physicians. They were able to see a decrease in the overall number of patients who left without being seen, despite an increase in the number of overall patients coming in, just by adding a total of 12 hours of coverage per week. And again, the issue, though, gets when looking at the entire emergency department. There are lots of interlocking queues. Your workup as an emergency physician depends on the queue for CT, depends on the queue for labs, and things get complicated really fast. When you start looking at multiple providers, things also get messy, even though some of these basic queue equations can work when you have more than one server, as you'd say. Sometimes behaviors get in the way and kind of change the dynamics. In particular, again, we emphasize that seeing a patient is not so simple. If you think about the workup you do, you're doing work on the front end and on the back end, and there's a whole lot of other stuff happening in between. You engage in a process called pipelining. In a sense, you have your own personal queue. You keep seeing patients until eventually something happens, and that something is usually you're interrupted by some other process. That CAT scan that you were waiting for on that first patient finally comes back. And it's been shown that emergency physicians tend to use their interruptions, even though we hate being interrupted, to help drive some of our workup, some of our productivity. In some ways, you go to see that first patient, you ordered the CAT scan, and in a sense, your encounter's done, provided there isn't something really terrible that happens and gets restarted again once you get the results back. So again, that interrupt tends to drive your workup. And as it turns out, you tend to build your own personal queue or roster of patients over the shift. Now, again, things are getting really complicated here. There are queues within queues. You contain queues, you contain multitudes. But how the hell are we supposed to model this? Again, there's already some complicated math we had to shoot through to get that single queuing calculator. How are we going to do the whole emergency department in one go? And then looking at behaviors, there are all kinds of other workplace behaviors that tend to really mess with those nice orderly queues. Things like social loafing, when you work together with somebody else and you're like, I just picked up a bunch of patients. I know there are a couple more coming back, but hey, my bud's coming on. I think they can handle the new incoming patients. Those sorts of effects tend to meld together and can really mess with those nice, neat models we have. So the answer, it turns out, is gambling. Something quite like it, Monte Carlo simulation. Now, Monte Carlo simulation is a very fancy way of creating a system which has the same sorts of characteristics, makes a lot of the same assumptions that those simple queuing models has. And then you basically create a system where you are seeing if a patient will show up, if a service will be provided with a virtual die roll. There's a probability based on those average times that things take, and you simulate whether a patient shows up at any minute or not. And it really flows kind of like a board game. Again, you can kind of imagine there's a big queue of patients going through the system, and each one of these different services can be a queue in and of itself. Now, again, the math to actually work out how this would work and give exact answers is incredibly difficult, and that's why people in industry don't actually do it. They run a simulation, they run a lot of trials, and then they average the results. This is bog standard for many industries out there, for transportation, for the service industry, whether it's from Starbucks, figuring out where they should place different servers along the coffee making process, or even in terms of getting packages delivered, how resources are distributed between one major metropolitan area and its warehouses and transportation to another. These simulation models are everywhere. And people have applied them to the emergency department. Now, here is a really fancy one called Two Point Hospital. It's for the general public. And I'll admit the graphics are pretty great, but I don't know how high fidelity in terms of a real simulation of the emergency department this is. Most of the time, the emergency department is thankfully not on fire. And we, as most emergency departments, devote very little of our resources to ghost removal. Certainly in terms of the graphics department, they've got it down. And there are a number of commercial software packages for professional industrial operations engineers to perform similar simulations. However, they also cost a lot of money for the end user. We're talking something like $10,000 a year for a site license, and that's assuming you already know how to program these things. So we set to the task. We took some of the models that we already had from studies looking at productivity, looking at throughput, and tried to create our own open source software model. Pictured here are some stock images of the college programmers we had helping us out with this project. So we came up with a lot of the guts, the research-oriented guts of the program using studies we had already done. And admittedly, we needed their help to get real cool graphics going. Unfortunately, we seem to have been hit by this thing called COVID, which reared its ugly head again during the graphics development period, and the college students were sent home. Instead, we've come up with this totally free open source version of the simulator, which I will demonstrate to you here. It's really not that hard to figure out, but it doesn't hurt if you know how to run things in Python. Again, our graphics department, we're really hoping for that multi-million-dollar grant to get those nice 3D patients. And you can simulate individual aspects of this system as you go. So again, it's not hard to see, at least in terms of looking at the long-term trends, how being able to simulate many pieces of this puzzle can be very helpful for looking at how making a small change, whether it's a change in turnaround time of about a minute or two, or whether, yeah, you should install that new fancy CT scanner, what's going to be the overall benefit in terms of how your department runs over time. You can go download this right now off of GitHub, or if you can wait for the summer, we're going to come out with a free in your browser web version with actual pretty graphics. So that's basically a very short primer on a free simulation model that you can use right now to simulate changes to your emergency department, as well as the the Q planner that you can use in your smartphone at edq.org right now. We are actively developing the software. We're soliciting input from emergency physicians, and I would love to hear from you what you think would be a useful feature, or things you think ought to go into the design that would be helpful for planning your emergency department. Did I mention it's free? Bill, go ahead.
So in the EMS world, there is similar software, and it has a name called System Status Management, where they try to match based on the time of day, hour of day, day of the week, resources to the call volume. So they have the right amount of units available based upon what's done. But they have found that this kind of system can be very demanding on the providers. So the question for you is, does this take into account your staff that you have in there and the increased workload, or is that a feature that is still to be built in? Because it's great to be efficient, but you also can burn out your staff in the same process.
Yeah, so that's a really great thought. So sometimes what is optimal on paper is not so great in practice. And so one of the real considerations we had when designing this was to actually look at putting in flexible physician behaviors. So I mentioned a little bit about social loafing. One of the big things that we've looked toward in operations modeling in emergency medicine is looking at the fact that robots are not a very good model for how people work in the emergency department, in that even though kind of we all have our own little queues and we keep going till we're interrupted, what can be a huge issue is the fact that you really just can't see the same number of patients late in your shift as you can when it's early in your shift. So one of the things that we're able to put in simulations like this is that we can put stuff like that natural decay into the simulation. And that again, compared to the mathematical queuing models, that's, if you tried to actually come up with a perfect solution for that, you would be doing integrals until kingdom come. When you run a software simulation like this, it's actually not that hard to say, okay, we're going to change the behavior. We're going to decrease the number of patients this physician can manage hour by hour, and then see how the simulation will play out.
Very cool. Yeah. I like your point about as it gets later in the shift or fatigue and how that impacts performance. Also makes me think of that's when maybe as you look towards modeling is to bring in the next physician, that acts as the transition physician, which is fresh and ready to work. So lots of interesting things, how to optimize things, I think, without burning people out is critical.
Yeah, and I think that is going to be the big piece of the puzzle that we help to contribute to, is that it's not simply enough to come up with the optimal solution, but it's got to be one that brings those human factors in. And I think again, from the EMS world, from the ED world, which is pretty closely related, I think that by having folks who are living and doing the work actually be the ones who are involved with the development of these systems, that's hopefully how we come up with a slightly more humane solution that's also efficient.